Well, welcome everyone. Thank you very much for joining us. My name is Ramon. I work as a developer advocate at Seldon, which is an MLOps platform. And we focus on the end of the machine learning lifecycle. By that, I mean we do model serving, model monitoring, and model explainability. So we do quite a few things. And we have currently four open source tools: Seldon Core, which is to serve models in production. It's a tool that sits on top of Kubernetes and allows you to create inference graphs. So for example, if you have a couple of models where one model depends on the output of other models, then you can connect all of those components and make it into one big inference graph. Then we also have MLServer, which here is the main website of Seldon Core, and we also have a tool called MLServer, which is for creating servers with machine learning, specifically for machine learning models, but you don't necessarily have to use machine learning models. And we will see a few examples of this in a little bit. So that's Seldon. We also have two more tools, which are called Alibi Detect and Alibi Explain. And both of them allow you to do drift detection and do all sorts of monitoring algorithms, or apply all sorts of monitoring algorithms to your machine learning models once they are, say, being served via MLServer or any kind of other tool. They're very much tool agnostic. And Alibi Explain allows you to explain machine learning models in many different ways. We have methods for counterfactual methods. We have compatibility with SHAP methods, partial dependency plots. We have quite a few methodologies in the Alibi tools as well. Okay, so that's Seldon. About me, I've been with Seldon for now about almost 5 months. Before that, I used to work as a freelancer. I was working with a couple of educational companies. I took courses in Europe, in the US, in Australia, all in data science, data analytics, machine learning, and a couple of courses in data engineering. I've been teaching at different conferences like PyCon, PyData, and the like for about 3-4 years now, and it's been a lot of fun. So I'm super excited to bring this workshop to all of you. All right, let me see if there's another question. Seems like I can use Seldon Core directly for model serving. What is the purpose of MLServer? Well, actually, so that's a great question. And so you can use Seldon for serving, but in the background, Seldon is actually going to be using MLServer to serve your models. So for example, if you see here in the, let's see, in the user guide, or in the inference runtimes. So if you see here, we have runtimes for all of these models. So say, for example, you finish training a model with scikit-learn, or you finish training a model with XGBoost or LightGBM or CatBoost. Well, when you finish training that model, you're going to have a couple of artifacts. Those artifacts are going to be, say, a Python file that loads in your model and that makes inference. Then you're going to have some requirements to be able to serve your model. You might also have server settings. So for example, what HTTP port are you going to be putting your using to for the URL or for the endpoint from which an application is going to hit your model. So all those things have to be set up. But if you use any of these models with Seldon Core, they're already pre-packaged, which means that you just need to tell Seldon Core where your model is sitting at. It will pull it from there, say, for example, an S3 bucket or a Google Cloud Storage bucket or an Azure bucket or whatnot, and then it will pull it from there. It will bring it in. It will serve it for you, and you don't have to do any additional tweaking. If you don't have that already, then you will have to create a custom model. And most of the models that we're going to be creating today are custom models, because these ones with our runtimes, you can serve them without writing, with very minimal code. But that's a great point. Can I already serve models with Seldon Core? Yes, you can, but you're already using MLServer in the background. with Seldon Core, and you're also already using Triton server, if you're if you want to host PyTorch models or TensorFlow models or ONNX, and so on and so on. Yeah, so that's that. So you're going to see a couple of directories and let me know if you can see my screen fine. You're going to see a couple of directories on the left-hand side. You won't see this directory for ML. And actually, I'm going to put it on my, where's my archive? I'm going to put it in my archive there. So yeah, so you're going to see you're going to have these directories here. You're going to have 1, 2, 3. You're going to have images, and then you're going to have a couple of requirements file, or one requirement file and one README file. In the first one, you're going to have a couple of files, servers, you're going to have examples, you're going to have templates, and so on. You're going to have a main.py, you're going to have a README, and that's okay. What I'd like you to do now is to open up the tutorial one. Don't worry about the tutorial.md or the markdown file. The one that we're going to focus on is in the Jupyter Notebook one. So once you come in, you're going to be greeted with a table of contents that has the things that we're going to cover here. So I don't want to read through too much through them, because that's mostly for you to go over when you have a chance. But it is important to say, like, what is the, to talk about at least the essence of this workshop. What is the point that we're trying to make with this workshop? What do I hope you walk out of here today with? And that's also available in the repo. If you were to see it, I think I put a couple of points there for that. Yeah, I'm hoping that by the end of today's session, you are able to create different machine learning microservices. Why microservices? What is this thing, microservices? Well, if you think about the way applications work or the way applications are created, you usually have a user interface, something that your users interact with. And let me see if I still have, oh yeah, I still have this one. Okay, so you're going to have a big application, and we're going to call it app. And then you're going to have a bunch of users. You're going to have a ton of users interacting with your application. And once they do interact with that application, there's going to be a lot of things happening in the background. Those things happening in the background are sometimes, or a lot of times, in the cloud. And that thing that we have in the cloud, so here we have, let's do user interface. And then that user interface is interacting with systems in the background that are in the cloud. If this user interface can sometimes be of two kinds. It can be a monolith, or it can be a set of microservices. And then the difference between the two is that when you have a monolith, you have every single component that makes up your application. Say, for example, I'm going to put component 1. So say, for example, every single component that makes up your application is going to be built entirely with the same application. So they're all going to live in the application. When you build your app, then everything is going to be put together, and it's going to be packaged, and it's going to be served as a UI. So if you make a change to any one of these ones, well, you have to make it to all. You don't have to make a change to all of them, but you kind of have to regenerate the application or rebuild the application completely, because everything is inside this big thing here. So you can't just go and access one of these components. But when you have a microservice, then you have a bit of separation of concerns. So let me copy these ones. So now, if this one is actually not performing well, we can take it out and we can have one of our developers. By the way, I'm quite pleased with the sticky man here that I created. We can take one of our developers. I'm usually not very good at drawing, but we can take, if all of these ones are working correctly, say, for example, we're going to make them green. They're all working correctly. And one is maybe so-so. We can have a developer say, check in the one that is bad and then try to fix it. And then we don't have to rebuild all the entire architecture of our application. That means that we can focus on fixing what's broken. And then once it's done, once we're done, then we can push it back into our application, and it's like nothing happened. Or not necessarily, of course, there's a lot of things that have to happen in the background for situations in which one of the components of your application breaks, gets pushed back in without any issues whatsoever. What people usually do, or what developers usually do, is that they go back to a previous version that was working, that had no dependency conflicts, and then they push it back in while they fix the issue on the newest version of the application. Now, once that's fixed, then we can push it back in, and then our application is working correctly again. And then we can say to our developer, well, now check this one here that is not working extremely well. Let's see what happened with that one. So that's the idea behind microservices. Microservices allow us to build applications where the components that make the whole thing are separated by design. So what about machine learning in this context? What is it that we want to do with machine learning? Why did I call this session Introduction to Building Machine Learning Microservices? Well, if you think about it, when we use applications such as, well, nowadays, the hardest thing is creative applications using or with the help of generative AI. So, for example, I use Canva every now and then, and Canva has a feature that allows me to write with a prompt, create a few images that I might put as assets to my my presentations or whatever it is that I am building. They also have different features. WhatsApp, for example, has a lot of things happening. And one of the things that I saw today when I updated or upgraded my version of WhatsApp is that you can now create stickers by describing it. I haven't tried it yet, but it said, tap here to create a sticker. I have so many stickers in my WhatsApp that when I try to scroll down, my application WhatsApp usually crashes. So I have to do it very carefully, and sometimes it takes me ages to be able to reply with the appropriate sticker because it took me forever to scroll slowly so that the app wouldn't crash. Anyways, what I'm trying to say with that is that creative applications or applications in different systems in different industries, they're going to have this multiple components factor. And those components, if say we have a team of developers, of data scientists, of designers, and we want them to be able to work asynchronously, well, we're going to give them different tasks. And we shouldn't have to wait till one finishes to be able to add an application or add a feature to our main application. We should be adding them as they finish. Sorry. So we shouldn't wait till all of them finish. We should be adding them as they finish. So one team might underestimate the amount of time that it's going to take them to build a new system. Another one might not. Another one might finish earlier. But there might be some testing that is required to be doing. So to be done. So anyway, so that's the point on why microservices are a good approach. Now, it doesn't come without caveats. Like I have here this this last sentence. Microservices, they can enable you to do faster iteration and more robust and resilient systems. Robust in the sense that if you have a team of 3 people building one thing as opposed to 10 things, they might focus more intently on building it, on testing it, and on making sure the application will provide the output that is required for the business. So the business level requirement. But at the same time, it requires more upfront design and infrastructure coordination. Who do we have working on this piece? Who do we have working on this other piece? And so on and so on. So that's a quick or brief introduction on the topic of today's workshop and what we're going to be covering today. But keep in mind that there's a lot of benefits on adopting a microservices architecture, but sometimes your best approach might be to create monolith applications. There was a blog post that I listened to a couple of podcasts that mentioned this blog post that said that is titled "Give Me Back My Monolith." So apparently, there are instances. Not apparently, there are instances where building a massive application with everything in it makes sense. Okay, so for the tools that we're going to be using for this part of the session, we're going to be using Fast API. Let me actually ask or check in with everyone. Has anyone here used Fast API before? Okay, we got a few people. Has anyone here not used it before? Okay, so we got one person. So that's fine. That's perfect. So hopefully some of you learned something new from this piece, but we're going to move from Fast API to different machine learning microservices, but we're going to start from the bottom up. Then we're going to write a little bit of HTML. We're going to do a little bit of Tailwind CSS. We're not actually going to do any Tailwind CSS. We're going to write words and hope that the description of it makes sense once we open up the page that has the CSS, because I am not a front-end developer myself. So it took me a while to put this thing together. Then we're going to use Generative, which is a user interface. Is maybe so. Most likely, a lot of you have heard of Streamlit. Some of you may have heard of Radio. Some of you may have heard of different tools that are out there for building UIs. We're going to be using Radio. I really like it. It's based on, I just recently found out that it's based on Svelte, which is a front-end framework for building interactive applications or for building web applications, period. Is based on Fast API as well. I think it uses Tailwind CSS as well. So very cool. And then we're going to be using Jinja 2 as well as a templating tool. I believe, I hope I wrote Jinja 2 correctly. If I didn't here, make sure you do install Jinja. I think it does get installed with one of the applications that we have in there. But if it doesn't, make sure you you install Jinja 2. Let's come back here. Okay, so what's the architecture of the application that we are going to build? So we're going to build an application with several services. First, we're going to have 3 templates. Those 3, so we're going to have a backend first and foremost. That backend is going to be built with Fast API. That backend is going to be pulling 3 templates. Those 3 templates are not going to have the machine learning models yet. They're going to have some sort of iframe, and this iframe is going to help us. It's going to help us embed a machine learning application inside our HTML, inside our page. Later on, in the second part, we're going to be building a ton of machine learning microservices. So this is the main idea of this part. We have a backend. We don't have a database. I thought it's quite a topic in and of itself to do the database part. Especially if we already have something that we can use on the front end to showcase how things are moving in the background. So we're going to leave that part, but note that is an optional, or that is a must when you're building microservices. You want to capture information of what's happening across microservices. What's happening with your main application, and also what your users are doing. Okay, so we're going to have 3 templates, and some of those templates are going to be talking to different services. Those services may or may not contain machine learning models. Okay, so what we need a backend, we need a front end, we need at least 2 machine learning applications. We might need some tests. We might need a database. So I put a little bit of wording here on what the backend is. I'm not entirely sure, or because I don't know the background of everyone in this room. I don't want to assume that everybody here has done a bit of backend work, but for those of you that have, you know that you are building the infrastructure that allows your applications, or the different components of your application, to communicate with each other. For those of you that have never done any backend programming, the best way to describe, or the way that I describe it to myself, is spin up a fast API server, use Ubicorn or Gunicorn to create different replicas of it, or to make them more performant, to extract, to enable the asynchronicity of this tool, and then attach a database to it. That's how I describe it to myself. Okay, cool. So we are going to use it today, Michael and Ramon. All right, so for the first one, notice that I mentioned we're going to be using Jupyter notebooks quite heavily. So make sure that you are you are opening the notebooks as well, because we are writing the files via this magic command that says write file, and then go into the example directory, and then write a file that is called jokes.py. Okay, so in a very straightforward way, Fast API can be used in the following way. So you can import from the main, from the package, you can import the main class called Fast API. This is going to allow us to instantiate an application. That application, we can use it to wrap, we can use that app object and wrap it around, or add it as a decorator to functions that are going to become methods. There are specific methods when we talk about microservices, or when we talk about applications that are going to be talking with one another. If they are going to be talking with one another, there's going to be different methods that they're going to be able to use. For example, here we have the get method. When we apply the get method, we say to our application, provide me whatever is in here. Whatever this function is supposed to do, when I send a get request to the appropriate link, to the appropriate URL, I expect to get as a return, in return, what you told me this function was going to do. Now you can imagine that a get method, or many get methods, they might be able to communicate with different applications in different ways, and in very complex ways as well. So in this one, we're going to try to start simple. We're going to use the PyJokes library to tell us a joke. So how do you start a fast API server? Well, the way to start a fast API server, let me open up my terminal here. Change environments. Okay, so the way to start an API, a fast API server, is with Ubicorn. If you have used fast API before, then you probably already know about this step. But the reason we use Ubicorn or Gunicorn is that they need fast API because it's asynchronous in nature, and that means that it functions off the bat with async functionalities. So if you write yourself a synchronous application, it takes a lot of thought to make it work correctly and to make every component work as intended. Meanwhile, FastAPI is what is called a ASCII framework, which is a synchronous server gateway interface server. So it allows you to handle concurrent connections efficiently. And then ASCII servers that can handle this asynchronous request processing, they need specialized servers. And two very famous ones are Ubicorn and Gonicorn. And they are used in conjunction with FastAPI and also with another popular API framework called Flask that some of you may have used before. So we're going to use Ubicorn, main, app, and then we're going to say reload so that we can reload our application. Could not import. Let me see, what did I name it? Oh, I called it jokes, this one. We're going to do Ubicorn let me move into the examples directory. If I'm in the example directory, then I'm going to do ubicorn jokes. So you're going to use the name of the file. So we named the jokes.py, and then you're going to do colon, and then you're going to give it the name of this application, the thing that ubicorn is supposed to run. Say app. We're going to say reload. Now we get to start our service, our server. So this is our first application. Let me see. I have a couple of things running in here in the background. Okay, so this is our first application. So if we take that URL, we come up here, we paste it, it's going to say detail note not found. And the reason for that is because that is not, we didn't say do anything with the root of the application. We said we want something called jokes. See, did I put jokes or joke? Joke without an S. So we put joke, and then so now we get, if we go to that URL, then now we get the joke. So we said there are 10 types of people: those who understand trinary, those who don't, and those who have never heard of it. Bear in mind that these jokes are not great, the ones that the PyJokes library gives you. But if we wanted to add something for the root of our application, then one of the things that we could do is we could actually go and open up the example, and we could come here to the example, and we could say, write another method. We could say app.get, get, say define, say hello, return, hello world. Let's see. And now if we go to the root, we should be able to see a hello world. Hello world. So that will be the difference in between the two, that when we say get, it's the same as going into a URL to get something. So remember, whenever you visit a website, technically the website is visiting you, because you're saying, hey, I want this URL to come to my browser. I want this a copy of this website to come to my desktop application, and so on. Okay, so that's Fast API. I describe a little bit here the main, how the main refers to the Python file, how the app is the instance of the application inside our file, and so on. And you can read more about it yourself. So also the difference between Ubicorn and Gonicorn. Gonicorn is a little bit more heavy duty. So it allows you to say immediately how many workers do you want to use for your application. So if you have a asynchronous application running, then you can always have it in 4 different workers or 4 replicas of that application running in the background. Okay, excellent. So we can send also requests directly from Python, as opposed to having to go to the web. As opposed to having to go to the browser, and then we get another joke. We get a response object back which says 200. 200 means okay. And then also in Fast API will also tell you if the request was correct or not. So if I was to say jokes, then it would tell me 404 that get request was not found in the application. So we can, so it's quite useful because it gives you some functionality off the bat, such as give me an error if this thing is not there. And also, you can also go directly to the docs, and it will tell you a little bit about what the methods that you have created are. So this is a string, get a joke will also return a string. Okay, excellent. So now that we have that part of the way, I put here a little exercise, but it feels like most of you have used Fast API before. I know Michael say he hasn't used it, and Ramon hasn't used it yet. So we have I put here a little exercise, but you can feel free to skip it because it might be a little bit too beginner friendly for everyone. And then we can focus on the next one, which is a little bit tougher. Okay. So now that we know a little bit about how to create APIs, how do they work, how do we get started with them using Fast API? But one of the things that we want to do is, if you remember back at the architecture of our application, is that we want to create a backend that talks to three different things. These three different things are going to be templates. These templates are going to be received from somewhere or are going to be pulled from somewhere via our API. So here we have our main file. And notice that if you open this one here, you're probably already going to see it populated, and that's okay. That's because I had already run this notebook to make sure everything was fine. You're already going to see it populated, but that's okay. And then what we have here is we have a get one because we're going to need, if you think about our website, we say we want to create a website that showcases machine learning applications. We're going to need a home where when people go to the URL that we give them, then they arrive at a place that explains what's happening in the background. Then we're also going to need one for the first service and one for the second service. And for the third service, if we continue going on and on and on and on. Okay? So now we overwrote the main.py file. So I can come back here and get out of the server or close out the server with Control-C that I instantiated or that I started. And then what we can do is we can use Ubicorn again. Now, from the main directory of the part of the session that we're working on, that is here, we're going to do Ubicorn. Now my file is now called main, and then inside of it is still the application is also named app. And then we're going to do reload. Okay. So notice that right now it doesn't have absolutely anything. So one of the things that it does have is this request thing. So it has each one of our functions. They return a request object. So when we send a request to our application, then we're going to send some sort of response back. And Fast API already has this request object that we can pass in, and off you go. Now it's ready to roll. So now we have our server there, but we don't have anything yet. Even if we go to this URL here, we're not going to be able to see anything. So I'm going to, if we come up here and we go to the root directory, we're going to see that it says no, because there's nothing happening. But we're going to come right back. So I mentioned we're going to need a home route, or we have a home route, a page with some service, and then another page with some service. So these three pieces here that you see, they're going to be like, say, for example, if you were to put this application in a production service, then this will be your cool website, and then the home page. Then this will be your cool website, service 1, and then your cool website.com, service 2, and so on. Okay, so let's talk about the templates. So what's happening here? I have this little template here. And if you have never done HTML before, HTML is the skeleton of a website. It allows you to do a lot of cool things, and it's extremely powerful. And one of the ways in which it comes alive is when you add scripts to it, or when you add a style to it. You can add style, you can get quite far with HTML. But usually there are frameworks and there are tools out there to make it easier to develop very sleek and very interactive user interfaces. So at the bare minimum, the things that you want to have in a template are, you want to have a doc type that says, hey, to the browser, this is an HTML document. This is a document that you not necessarily have to have actually the language English, but it's better if you do. It's best practice if you do. Then your application is going to be divided into different things. And those things are going to be the head. So the head is going to have metadata about your application. So for example, it's going to say, it's going to have a title here. So I believe that right now, if you go to the, okay, the title is not, yeah, I'm not pulling anything yet. But once I do, at the top, instead of seeing 0.0.0.0 or localhost, you're going to see building machine learning microservices as the title of my application. Then also we can pull in different components from different places. So for example, here we're saying, hey, I want to use Tailwind CSS as the style sheet for my website. So please pull that from wherever this URL is pointing at and bring it into my file. Then we're saying we have a couple other things. We have the body, and then inside the body, you're going to have usually different components. Most websites are going to have three things. They're going to have a header, they're going to have a body, and they're going to have a, or not a body, but a, I forgot the name of the middle part, a main part, and then they're going to have a footer. But you don't necessarily have to do it. Once you are inside the body, this is the thing that's going to be displayed in the in your application. So here we have something else called a div. A div is a container. This container is going to take some space inside inside your application or inside the browser when it gets displayed. And then inside here, you can give it different things. So here I have an H1. H1 is the same as a title level 1 in Markdown. When you do the hash and then you put a title, that's going to be similar. So here you see this is a title level 2 in HTML that goes with tags. And also you have to remember that whenever you open a tag, whatever you put in it, so for building machine learning microservices, you have to close it as well with a special, with a little forward slash in front of the same name. So then to every one of these components, you can add a class. That class is going to say, I want the font to be bold. I want it to be of this size. I want the text to be extra large. And so I want this class to be of this. I want this to have this thing in here. So this is a title. This is a paragraph. And then next to it, we're putting a button. So once we create this, we override this template, the home template. Then here's a bit of explanation of what I put. What it's going to do is going to have two buttons. Those two buttons don't do anything yet, but later on, they're going to do something. And all they do right now is that they display two names, Microservices 1, Microservice 2. What we want to do in order to be able to use it is we want to override our application. And we want to say, we want to import Jinja 2 templates from Fast API. And then, so we still have the same application being created. Now we say, hey, I want you to grab this directory as the place where I'm going to put all of my templates at. So if you notice here, I have page 1, page 3, page 4, and so on. And then I have a home. So what it's saying is this directory is going to be used to return some sort of template back to the user. So here we're using the templates, and then we're saying we're going to provide a response with the template that we just created above called home.html. And then we're going to return a request response. So if we overwrite this, we look at our application will get reloaded. And then, so changes, watch file detected changes in the main.py, so reloading the app. So now if we go back here and we refresh it, now we can see, and this is at 250. Now we can see that we have two buttons. Those two buttons, they don't do anything right now. So Microservice 1, Microservice 2, and then, but you can see that they look quite nice because we're using Tailwind CSS, which is a nice CSS framework with a lot of components already built up. So when you use a class method, such as this one's here, you're inheriting. So the body is inheriting from this tile sheet inside the head of our HTML file. Okay, so that's perfect. So we can reload it, we can open it again, but now we have the thing that we wanted to see, which is the building microservices, building machine learning microservice. And then your description goes in there. So we're not going to bother with that. Let me see if I have any questions. Okay, everything good? Okay, so now we're going to be creating our first service. So what is our first service going to be? It's going to be a page where when we load the page, we're going to have a button, or where's the button? The button is input, checkbox. Okay, so we're going to have a little box that has an input and it has a checkbox. So whenever we click that checkbox, it's going to launch a button. That button is going to bring a iframe into the scene. And I'm going to spare you the details of all of the CSS because I am not the best either at it. I found an example that I walked through where I could write something nice and put it as a part of the demo for this one. And then I ended up tweaking it and making it look the way it looked. So we have, again, the head, which brings in a lot of things that are going to be inherited by the body of our application. And then inside the body, we have one container. And then in that container, we're going to have another container that is going to bring a iframe or an application from somewhere. So now we said templates one. We created templates one, and then we're going to notice that we are not overwriting. So here in this piece, we overwrote that file that we have with Fast API. But then now what we're doing is we are appending a new method with a -a parameter, and we're saying service one is going to return a response with page one.html. So now that we appended this here, file detected, main, okay, there it is, reloading. So if we go back up, then we come up here, we still haven't connected those buttons, so they don't do anything yet. Service. Notice that we now have a component here, and you can make sure, you can check that it is a component by clicking on it. So for example, you can see if you right click on it and you click inspect, you can see that there's a div, there's a thing that we created, the container, the padding that we gave it in relative to the browser, and then the little pieces that are in there. Okay, so what are we having here if we click launch ML app? So what we have, so there should be here a spaces. So what I did was that I picked a Hugging Face spaces. So say, for example, if I come here, recognize detect segment, and we click on the three dots on the top, and we say embed this space, we're going to see the source. And if we take that and we add it to our template here, and Fast API is going to reload. There it is. Then we can come back here. Okay, so the little iframe didn't work here, but we can, technically speaking, put any kind of website, and then make it so that our application showcases that website. So I have another example here where we can create a service from our computer. And then once it comes up to http://localhost:8000 service one, then we can embed that and also see the iframe in here. The idea is to build a skeleton, to build an intuition as to how we will build microservices. So we have an application sitting somewhere that we haven't built. We will build an application in the next notebook, in the next section. In the next two sections, we'll build two applications. But right now, we're taking components from different places to build an intuition as to how we will go about making microservices. So I'm going to move along, and then we're going to find another example that we can put in here instead of this one. So let's see if I actually do machine learning. See what happens if I put this one as my page one. Developers that google.com refuse to connect. Okay, I guess I need to pick an even easier page to be able to embed, but you get the idea. All right, so now we can create our own application. To initialize, we can create a radio app with a little bit of music, or any kind of radio app that does something such as say hello to a person. So here I have an example taken from the documentation. We do have a much thorough example in just a little bit. So see the application here that we have called ML_app. If we go to the servers, we say radio space ML_app. Beauty of live coding. Yeah. Okay. So now we have a little app. Posted in here. And if I put hello Ramon, then it's going to say hello Ramon. So nothing fancy, nothing ridiculous. We're going to substitute it in our application. And we're going to come back here, and now we can see that the application does come up. And imagine if this was a machine learning application, then we could say, hello, MLOps world. And then it will come up, something will come up on the other side. So if this was a language model or something similar. Okay, excellent. So let me see if I have a question. Nothing. Okay. Perfect. So now that we can see that it does work. So one of the things that we can do, we can create a second service. And then in the second service is going to look exactly the same as the previous one. And it's going to have an iframe. The following argument requires a file name. Oops. So in this second one, you're going to have to put at the top write file, and then in templates, we're going to put page2.py. Now we wrote it as page2. So then we again add to our fast API application. We add a new method. We call it service2, and then we say, hey, page2.html is the page, is the template that I want you to return to users when they come to this website. So if we come up here and we go back up, so we can go, instead of service 1, we can go to service 2. Let's see. And this is a page2.html, not a page2.py. In case you did the same one I did. I also attached this service to twice, and there was no need for it. So you can delete it if you did the same as me. Come back here, and then let's go back up. Now we have, before we had a green button, now we have a blue button, and then we also have the exact same layout that we had before. But again, this is building the intuition. Then the last thing that we want to do is that we want to add ways for the main website to be able to have, for us to be able to click on the main website and say, I want to go to this one, or I want to go to that one. And the way in which you do that is that you can do that with an A tag, where you assign a href or a hyperlink reference that can take a file path, or you can take a URL. So here we're saying, when I click this button, I want to go into this page. So then the button is inside of it, and then we have the A wrapped around it. And then we do the same with page 2. Now we overwrote our home template. If we come back here and we go to home, and we still have these 2 buttons here that look quite nice. But if we click in Microservices 1 or Microservices 2, so this one is meant to be service 1, and then service 2. Then if we come back, now we can go to service 1, and then now we can navigate to service 2. And both of them, even though they look a little bit different, they both have the same thing inside of them. So we can go back, go to Microservices 1, launch it, and so on. And that's the idea behind building microservices. We have different separations of concerns. We have somebody could be writing the templates, a front-end developer, and they will add scripts to the templates to make them even more interactive. Data scientists will be working on the machine learning models. Maybe a machine learning engineer will be working on the models. Then somebody else will be building a little UI, or the DevOps engineers, they will be building the infrastructure, and so on. So there will be, the idea is that there will be different people working on different things for your application. And this is the end of the main example. I put some ideas or some things here on how to do testing. Testing is a topic in and of itself, as in the same fashion as doing databases is. So I put a little section here where I explain what kind of tests you could do with your application, and then I give you some examples as to what you could do. So for example, here we could do import PyJokes, get a random joke, and then make sure that this works. And then we could have a test that says, hey, test, did I get a joke? And then if this joke is instance of a string, then, and if the string is greater than 0, then that assertion passes. So this will be one test that we would do to the first story example that we created. In the second one as well, we could say, hey, test client from fast API test client. We could say test. We could test that we are actually getting the status code of 200, that we're getting a JSON response back, and so on. We could test the endpoint. We could do error handling. We could do a bunch of cool stuff to make sure our application is robust, as robust as it can. So let me see if I have any questions. Oh, Michael said it's because it was page 3 in the template folder. I used to before running the override. Yeah, I used to before doing the override. So I had a few templates there because I was testing different things, and I ended up committing all of them to the repo. So everybody should be able to see all of them. But the idea was to recreate them from the notebook. But it's fine. If it works as intended, then that's totally perfect. Okay, so I have here a quick exercise, and I put find an HTML template online and add it as a new file to the templates directory. Again, I think this is a little bit very introductory for the crowd here. I had it as a fun example that we could have fun with, but maybe it's best to focus on the second and the third part, which have a lot more content to go through and a lot more models to go through. And now, before we go on the first break, one of the things that I love for everyone to do is if you could open up the tutorial notebook in the second directory in 2ML web app part 1, and make sure that you can run these first two cells, because it is going to download a model for you, and that's going to take a little bit before we go on break. Then it would be great if you could start that by downloading that model already. So make sure that you run this second cell, and you can leave it there running. What we'll do is, it is 1:10 p.m. Central Time. So we're going to go in a 10-minute break. So come back here at about 1:18, and then make sure you get up, stretch, go grab some water, go grab some coffee, and I'll see you back in 10 minutes. Okay? If you have any questions, I'm going to be here. But again, make sure you run the first two cells of the second notebook in the folder, in the directory titled 2ML web app part 1. Welcome back, everyone. This is the fun part of the session. Now we're going to start dealing with music. We're going to start building music from nothing, using songs to create new songs, or tweaking songs by, say, increasing the volume, retracting different components of it. So yeah, so this is the fun part of the session. Make sure that if you haven't already, make sure that you run these first two cells of the second notebook in the second directory in 2_ML_ web app part 1. The reason is that this is going to take a little bit depending on your internet speed. This might take a little bit. This might be quite fast. I don't have the absolute best internet where I'm staying at, but it still works fine. So yeah, make sure you do that. And if you get any kind of errors, remember that you have to have something that is crucial, is that you have this FFmpeg application installed. It can be installed on any platform, Linux, Windows, Mac. So make sure you do have it. And if you have a Windows, you can go to ffmpeg.org and then download it for Windows there. Okay, let's go and get started on this side. All right, so we talked a little bit about microservices, but we talked quite a bit about microservices. We built toy application. We built a front end for it. We had Fast API as the backend, bringing in the templates, and then the templates in and of itself, they had different iframes that were showcasing different applications. So it was sort of application, 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 application. And then all of those, the nice thing about all of those is that they could all be separated. But then if we talk about machine learning in the music industry, how is this used for? How is machine learning being used in the music industry? Also, how big is the music industry? So if you think about the music industry is a multi-billion-dollar industry where companies, so like any kind of company that you can think of, needs music. So say, for example, gaming companies, they need specific kinds of musics to or songs for particular games. So for example, if you remember the Super Mario song, whenever you were playing Super Mario, then nobody can ever forget about that. But that had to be created by someone. And those tools are built on top of programming languages. So if these things are built on top of programming languages, and how does machine learning how is machine learning used? Because we know we can create machine learning applications with programming languages, but we're usually doing it on top of data. Well, the reason is, or the main reason why we can use machine learning for audio applications is because we have to talk first about what is audio. So audio, if you think about it, say, for example, we have, here. Say, for example, we have a person here. That person says something to someone, and then that something is going to travel through air. And then say this other person, this was via a phone. I should have said this person has a phone here, and then said something to someone. And then this travels via air, or maybe this person doesn't have a phone. Maybe this person is just yelling to someone. How does this other person on this side how does this person here listens to that? Well, sound is vibrations in the air. So if we decompose this and we take it a step further, so sound is going to be, oops, that last one was not great. Sound is going to be vibrations in the air. These vibrations in the air have specific characteristics. They have a frequency. So how long do they go for? So for example, if I do that, or if I speak and I get louder, well, how long can I maintain my a note when I speak? So this is going to be time. And then here we're going to have something called amplitude or intensity. And then in here, we're going to have waves of pressure. And in between these waves, we're going to have different frequencies. And then those frequencies are going to be represented as numerical values. And then these numerical values, like for example, 0.4, minus 0.3, and so on, all of this is going to be taken into an array, and then that array.
Hey, Ramon, you're currently just sharing a window that's like in an inception view for everyone to see right now.
Oh no, I've been talking about a bunch of stuff and I didn't realize it. Oh, I'm very sorry.
That's okay.
I thought I was sharing my entire screen. Okay, here it is.
Let's get that all sorted out.
Okay, can everybody see my screen fine?
Yes, now we can see.
Oh, I have been doing my best drawing ever so far.
I'm going to jump back off.
Okay, no problem. Thank you. All right, so I mentioned that. Imagine we have a person here, and then this person talks. That talk or that sound that that person is making becomes vibrations in the air. These vibrations in the air are detected by our eardrums and decoded in some sort of way that I'm not going to tell you that I comprehend exactly how it works inside the human body. But what I can tell you is what happens when it becomes digital audio. So audio is the digital form of sound. Sound is pressure in the air. And then this pressure can be put in a graph. In this side here, we have the amplitude or the intensity. And then in this side here, we have the time. And then in here, we have the frequency with which it happens. So every time, if we capture sound at those frequencies, when it goes up, when it goes down, we can put all those pieces of sound in arrays. And then that array becomes the data that we can use in different kinds of applications, in particular, like machine learning. When you have one of these arrays are going to have a ridiculous amount of values. So for example, one song of about 30 seconds might be 1 million points or so. I'm putting a number. out of my head. And then the missing piece of this is that you have to have some sort of frequency and measure in hertz. And then those hertz are going to be when you take all of these numbers. Say, for example, here we have maybe 1.3 million files. And then we divide them by some common frequencies that are used are 16,000, then 44, 100, and 32,000. So then if we divide this by one of these numbers, it has to be sampled in a particular frequency, then we're going to get the minutes. So say, for example, 4.3 minutes of a song. So in essence, and I know that my drawing is not the best one, we speak, we sing, we create melodies. Those melodies become sound or become vibrations in the air. Those vibrations can be captured by systems that we create with programming languages. Those systems take the amplitude, measure the amplitude, they measure the time, measure in frames or measuring in seconds or measuring different things. How long do we speak? How long are we singing? And so on. And then at every single point, we're taking a specific number attached to that vibration. And some of those numbers are very difficult for the human ear to listen to. And some of those numbers are going to be too high pitched, so they're going to be very disturbing to our ears. So then we measure all of those points along an axis. Then we put them into an array of some sort. That array has a specific amount of numbers. We divide it by a hertz, some measure. We divide it by that, and then we get the minutes. We get, see, if it's for a song, we're going to get the amount of minutes that we're going to have that tune or that sound being played. So in here, we are using, here we have what is called, we're going to go right into an application of music with generative AI. This particular tool here, this particular model here is called MusicGen. MusicGen was developed by researchers at Meta AI and is a, click here, MusicGen, let's see if this is the one. And it is a type of language model that, or similar, it's kind of interesting because it's music, but it's also a language model, but it isn't, but it is, but it isn't, but it is. And it's using the architecture, the Transformers architecture, and it kind of makes you wonder, how the heck is this happening? The mechanics of exactly what is happening inside of MusicGen are outside of the scope of this, but that doesn't mean we cannot have a little bit of fun with it. Let me see if I have a diagram here. I'd say in the paper, they will have a diagram of it. But so, for example, you can describe what MusicGen does. It gives you two things out of the many. But one is you can do text and create music. So you can go text to audio. And another one is you can do text conditional on audio and then to audio. So you can have a song that you really, really like, and you want to describe another song that you wish existed. If that song, then that song that you wish existed is going to be based on the one that you gave it. So you have, say, Britney Spears' Toxic, and then you want to create a melody from Bach or from Beethoven, and you want to create a melody similar to theirs, but you want to have it with the style of Britney Spears' Toxic. So you add the song of Britney Spears, you describe the one that you want to create, and then the model will resample from a distribution, then create this particular song. And then let's see if we can actually see. Not to get too deep into the paper, but it has different diagrams of how the architecture is working. Let me see if I can find one specifically about the architecture, even though that's not the main piece of it. Not necessarily, but it's okay. We can have a look at what they're doing. So here we have a dynamic blend of hip hop and orchestral elements with sweeping strings and brass evoking the vibrant energy of the city. So this is built by MusicGen. This one is by Music LM, one built by Google. This one is by Refusion and by Muse AI. I think the reason I didn't see the paper in this one is because I didn't go to exactly the one that I needed to go. But that's okay. We're not going to waste. We're not going to stay too long in here. Another one. So melody is conditional on something else. So here is a source of melody. And then here is a description, an 80s driving pop song with heavy drums and synth pads in the background. That's quite nice if you think about it. This was kind of like very sinister song that you will see. I can't remember from where. And then now you add an element of this pop element of the 80s. Here's another one. And then an energetic hip hop music piece with synth sounds and strong bass. There is a rhythm, a rhythmic hit hi-hat pattern in the drum. That one doesn't sound quite great, but the idea is that you can create stuff from nothing. Okay, so now we have our two classes. We have the auto processor, and then we have the music gen for conditional generator. The auto processor is going to take, both of them are going to take in the exact same model. One is going to take the weights or half the weights. One is going to have the processing steps for the text that we want to produce. So here I am from the Dominican Republic, so I love bachata, I love salsa, I love merengue. So here I put a fast bachata with high quality in the style of Juan Luis Guerra, which is a major singer from the Dominican Republic. So here I put padding true and return tensors. Padding is the concept that if any of you have dived deeper into transformers or into natural language processing, you know that when you are processing pieces of text, every single piece of text, every paragraph, every document is going to be of different lengths. And sometimes your context or the length that your model can receive when documents are transformed into numerical representations are going to be of a specific cut. If your description doesn't make that length, then you're going to pad it with something else towards the end. If your description is before, then you're going to truncate it so that it stays within the boundaries of what your model can fit. So we have here a piece of text. We pass it through the processor. We get the sampling rate. Remember, we're always going to need when we get a piece of text, or when we get a piece of data, and in particular sound, we get a bunch of numbers. When we get those numbers, we're going to want to have the sampling rate so that we can then condense them back into something that sounds like music. So here we have the sampling rate, which is 32,000. And then here we have the audio values. So here is where our model is going to be put into work. So in the inputs, let's actually evaluate what the inputs are. For the inputs, you're going to have input IDs. So there's an embedding space or a space for where every single component or every single token can be mapped to something else. And then there's also an attention mask. So what should the model be paying attention? So the way transformers work, or in natural language, is that, or the way in which text processing works for transformers is that you divide every piece of text into a component. Sometimes a word might be one token into components called tokens. Sometimes a word might be one token. Sometimes a word might be two tokens. Sometimes, and so on. And then you create a space where you can map everything that could be written. You can map it to a like a document database or like a dictionary. Sorry. So then now you have these things called tokens, and you can divide text into these individual pieces of token. So how do you do the same when you have audio? Well, the idea is that when you have audio, you turn these representations into, so remember this graph here, you're going to turn it into an image. And that image is going to be of a spectrogram. And that spectrogram is going to have different vibrations or different magnitudes, where we're going to see when the sound goes up, when the sound goes down, what's happening, but in a continuous space. So when we have an image, now we can partition it into little squares. And then those little squares, and actually I can show you here. So imagine I have this image here, and then I partition it into these little pieces. And now each one of those pieces is going to become a token. So token 1, token 2, and so on. And this is going to be synonymous to, say, for example, let me add some text. This sentence will be tokenized. So now, each one of these components will become a different token. And here we're going to have T1, T2, and or token 1, token 2. It might be hello, it might be sentence, it might be token, might be split actually into, I don't know if this is true, if token will be split into token. Either every model has a different token, or not every model, but a lot of models have different tokenization methods. So this one here is going to be toke, and then this one here is going to be tokenized, and that's going to be 2 tokens. So then in the same with the image is, so the audio is going to be taken from raw data or raw values. It's going to be put into an image that is going to be called a spectrogram. That spectrogram is going to be divided into pieces, and those pieces are going to become the tokens. Those tokens are going to be put right next to each other in a sequence. And so on. And that's a bit of intuition behind it. So this is where you have here what each token represents in the dictionary of tokens that this has, and then where should it pay attention to. So now we have the sampling rate. Now we're going to be generating a piece of music. Now you have a couple of things here. You have something called guidance, scale, and then you have something called max new token generations. So max new token generation is going to be synonymous to the duration of the song. So in the previews, in the main repo that Facebook released with MusicGen, the tool was actually called AudioCraft. And in AudioCraft, it will have a piece where, let's see if we go script, test, examples, demos. So the tool will have a piece that will be called duration. So here duration will be 0.5. Get bip bip. Duration will be 0.5. But if you add it, if you bring that up, then it's going to be synonymous to seconds. In Hugging Face, or the implementation from Hugging Face, we have something called max new tokens, and that's also that the higher the value, the longer the song. The lower the value, the shorter the song. So now notice that we have a tensor of 3 dimensions. We have what will be a batch, and then the dimension of the song, or the channel of the song. This is a 1 channel. So another thing that is common in music, you might hear 2 channels, because a lot of stereo systems will have 2 sides to it, a left and a right side. And so often both sides are completely the same, more often than not. But sometimes there's songs that they only apply a specific rhythm to the right hand side, and then there's songs that only apply, and they might apply a different rhythm to the left hand side, and so on. So it is dependent on different things. So we don't want this as a torch tensor. We want it as a numpy array, and also we want to take from the first batch. We want to take the first. We want to take the first batch We want to take the first element. We want to take that array. So now it's going to become one array or one channel of these values. So this here is going to be quite short. This is probably going to be about 5 seconds. But we imported earlier the audio module of the IPython library. And that means that we can take that array up there, pass it in here, tell it the sampling rate, and then it's going to reduce that song to its main component. So that was the bachata that it came up. And then notice, remember that the sampling rate that we're using is of 32,000. What do you think is going to happen if we make it half the size? What do you think is going to happen if, what do you guys think is going to happen if we decrease the size here from, where am I at? From 32,000 to 16,000. Do you think the song is going to be longer or is it going to be shorter? It will be twice as long. Okay, let's see. And that's correct. Yes. It will be twice as long, and not only will it be twice as long, but it's also going to be slower. So because now we're trying to kind of expand it and so on. And then if we want to make it faster, then we reduce that. So that helps us build the intuition behind the amplitude. Whenever we are taking in those values and we get this array of many, many numbers, and we divide it by the hertz, 16K, for example, then we're going to get the seconds or minutes, however long that thing might be. Okay, so that's correct. It actually sounds, I don't know which one sounds better, but anyways, we can also do a couple of other things. Librosa is one of the main libraries, I would say, in Python for audio transformation and effects and a lot of cool things. There's a lot of cool things that you can do with Librosa. And one of them is to add effects to the music that you are creating. So here we have the same array that we created a second ago. And then now we're going to play it. We're going to play it back with the same sampling rate. So let me put it back. The song that we created. And now with an effect applied to it. It sounded way more suppress the sound, almost like if it wanted to break out of a prison or something like that. But anyways, that's one of the cool things that we can do with sound. Now there's another tool called Pedalboard from Spotify, and Pedalboard is very, very versatile. It allows you to do a lot of things with audio, and I really like what the team at Spotify has done with this. It has a lot of classes that apply effects to music, for example, such as distortion or delay or reverb. And then it also has a nice way of reading in files. And these files go straight into NumPy arrays as soon as we read them. So let's give an example. Let's go through an example here. There is a song in your directory. Here's the song. Let me turn it down a little bit. So that's the 30-second clip that we have here. So we're going to read it, and then we're going to get two channels. Remember, a lot of songs, in particular, come with two sides to it, and more often than not, those sides are very much alike or very much the same. You can tell here that earlier we had about 600,000 numbers, and now we have about 1,000,000.3 because the song is from 5 seconds to 30 seconds. It's about 6 times larger. So then here we have the song again. But let me play it maybe at second 5. And then if we want to apply different things or different effects with pedalboard, we pass each one of those classes. We have to create an object called pedalboard. And then we pass each of these classes to it. And then we can change all of these elements. We can delay it a little bit, add some feedback, add some mix to it, add the reverb or the room size. Like, does it seem like this? There's some echo as if it was in a room or not. And so, by the way, I'm not an expert on audio processing or anything of the sort, but it was a lot of fun to put this workshop together. So now I put it, instead of 32, say, for example, I should be using the same sample rate that this one has. And let's see, SR. SR for this one is 44,100, but you can still apply those effects at a smaller sample rate and have different effects to it. So I'm going to put here the actual one, and let's now see what it does. It sounds a little bit more rough, as if it was live, the song. Now, if I put it at 16, it sounds a little bit more clear than even the original one. Now, if I did it at 16. So different ways of applying effects to music can be also tweaked when you apply different sampling rates. Okay, so if we wanted to save our creations, then we will create a directory and we will call it music. And then with audio file, you can open up a file or create a file that's going to be open, and you're going to write to it. You put the sample rate that we are using, how many channels you want to do. So you don't have to save 2 channels, even if you have 2. You can say, hey, I only want to save 1. The song is the same in both arrays. So that's just taking a lot of, that's just making the file even bigger. So why don't we save some space? And then we're going to apply it as, we're going to call it F, and then we're going to say write, and then we're going to pass in the new song that we created with pedalboard. What happened? Let's see. I have expected shape. It has 2 mono. Able to determine the shape of the audio input. Expect 1 channel audio. Okay. So here we put the 0. Now we save the song. This is the channel that is expecting, or the channel that we're using to save it. So here I said, yeah, take 1, and then now we saved it as a mono sound. Okay, so now what if we wanted to use, because we liked this song, let's see, because we like this new song, not particularly fond of the song, but, or say, for example, we want to, actually, that we want to use the one that we created earlier with here. Say, for example, we want to use the one that we created with Music Jam, and then we want to pass it in, and the sampling rate has to be the same, or it should be the same, 32,000. So we're going to use this one. And we're going to pass it here. Remember, we're going to use the song that we created earlier, the fast bachata. And now we're going to say 80s blues track of groovy saxophone. So we're going to we want to create something that has a saxophone in it. And actually, I'm going to put violin notes. 80s blues with violin notes. I'm going to use the fast bachata from earlier, same sampling rate, and then I'm going to create a new one, a conditional song on this one here. I'm going to put padding true and tensor true, and then I'm going to get new audio values. It's expecting 1 channel. So we got to take Let's see, expected mono audio, but example has 1 channel. Okay, so we're going to take the first one here. Now it's creating our song. So some of these methods or some of these tools, they're going to be very finicky. Some of them will only take the song if it has 2 channels, and some of them will only take the song if it has 1. So that's quite interesting. One of the tools that we're going to use in a little bit can only take 2 channels, and they can only be PyTorch tensors, which is very a little bit limiting, I'd say, but it's fine. If you find yourself in the situation where you don't have 2 channels to pass in through a plugin or something similar, then you can always duplicate the array, and now you have 2 channels. Also, it's important to bear in mind that when you are creating conditional on another song, then it might take a little bit longer. Also, I am not running this on GPU, even though I do have one. That will make it a little bit faster, but I'm running it in my machine, and usually it doesn't take this long. But in the next section, what we're going to be doing is we're going to create a microservices architecture with 4 components to it. One of the components is creating new music. The next component is going to be creating or visualizing that music. So, for example, my failed attempt at creating the visualization on how sound gets created or converted into audio, we're going to create a visualization like that with a comic theme to it, the XKCD one. Then we're also going to create a spectrogram, which is the representation of audio that becomes an image. And then after that, we're also going to, so the first one, create a song with a description. Second one, create visualizations of those songs, of those new songs. Third one, apply effects to the visualizations. And fourth one, create a different representation of that music so that we can tweak the song that we created. Okay, so here I have the new audio. Let's see. That was quite nice. And as you can see, it kind of starts with this one. It's conditional on that one, but it kind of took this one in, and then it applied a few effects of 80s blues with track, with violin notes, and so on. I wonder what it would have done if I would have done the saxophone. But as you can see, it starts pretty much the same. And then it goes on with drums, but I could never tell whether there was any violin whatsoever in it or not. And that's okay. But that was a cool thing to see that we can do with it. All right, so time to get our services up and running. So this is the first time that we're going to start creating machine learning microservices. So there's a few things to keep in to notice. We're going to be using MLServer. I mentioned earlier, is one of the open source tools that we have at Seldon. And the reason I like it in particular, even before I joined Seldon, it was that a lot of companies are using Fast API, or a lot of tools are using Fast API in the background or as part of their tool to create a microservices. But what if we wanted to create a very highly performant one on top of Fast API? So MLServer is using Fast API under the hood and is using its own implementation to create a handler that takes in requests from different places. So it's highly performant, multi-modal serving tool that anybody can use in a relatively straightforward fashion. And so that's what we're going to do. So we're going to create a file, and that file is going to call MLService, ML_service. It's going to be inside the servers, inside the ML_model. So we're going to have it here. Again, separation of concerns. Another company, another team, you might treat your applications differently. You might have different repositories. You might have a giant monorepo. So here we have it all in one single place. So we are adding from the MLServer package, we are extracting the MLServer class, the settings, the model settings, the ML model, and then from the MLServer codecs, we are extracting the decode args. You're going to see why in a little bit. Then in the same fashion, we imported the transformers library or the auto processor from the transformers library and the music gen conditional generation, we are importing them here. We need NumPy. We need typing. Fast API is works very nicely with types. And because MLServer uses Fast API under the hood, we can also take advantage of that. And then we're going to need the async IO module, because when you run asynchronous applications, you are creating a event loop, or a loop where your application is going to be listening to requests, and then it's going to take them, it's going to run them, and then it's going to go back to its normal state. Okay, so then here we are appending the main method by which we are going to create the model. So if some of you have used different tools for serving models, some of the tools that are open source out there, some of the tools, a lot of the tools follow the same recipe. And that recipe is load a model, load the weights if you need them, and then create a predict function. Sometimes those functions are going to have, or those classes are going to have a function called pre-process. And then sometimes those classes are going to have a post-process function. And then you might apply that pre-process function here as soon as you receive some input. And then sometimes you apply that post-process function here before you return the input. And this is very useful because you can get very, very creative with the things that or you can have, not necessarily creative, but you can have a lot of flexibility with the things that you can do to your input data and the things that you do to the output data that you're going to return. So here we have the same things that we did earlier. We are creating the auto processor with the name of the model music gen, and we have self here so that we can pass it into other methods. Then here we have the model itself, and then here we are taking in. Notice that we are taking in some text, then the guidance scale, and then the max new tokens. Notice that here I put NumPy array and NumPy array here as the input, not because we are expecting an array of values, we are only expecting a scalar, but because MLServer follows a specific standard for doing inference, which is called the Open Inference Protocol, or the V2 Inference Protocol. And we're going to see in a little bit what that actually means. So, okay, we're taking the text, a list of strings, the description, we're adding padding, we're returning a tensor. Then we're generating the song in the same fashion as we did earlier. Because we are taking in a NumPy array, we are going to take the first row, the first element, first row, first element, and then we're going to take the sampling rate. And I think I had it here to do something with it, and I don't remember exactly what it was, but we can take it. We can take it out too. Doesn't really matter. At least we don't need it right now. And then we're going to return the audio values. Okay, so then the last piece of it that we are also appending is a main function. So we need some settings. Here in the settings, we could be passing, for example, HTTP port. And then we could say, instead of being 8080, we could say 4040 or something like that. And then, and I'm actually going to take, I'm going to take that out. Server-wide settings into your settings class. Then in the second one, the MLServer, which is going to be your main class that's going to run your model, you're passing in those settings for your server. Here you can put a bunch of stuff. Then you're creating a model setting, a model settings class. You're giving that model a name. This is what is going to become part of your URL. And then you're adding an implementation. The implementation is going to be the name of the class. Remember, similar to what we did with Fast API earlier, where we have an app object, and then we pass in that app when we call Ubicorn in the terminal, or when we call Ubicorn inside a Python file when we want to run our app. So here we have the name of the class. Then here, this becomes an object called model settings. And then we pass those settings inside the server, and we start the server. We have to put in, notice that, remember, because his MLServer is completely async, then that means that we're going to have to await. We're going to have to use the await method when we have asynchronous applications starting. And then lastly, what we're going to do is that we're going to use the async.io module, and we're going to create an event loop, or we're going to get the event loop that is going to be started by this process. Then in that loop, we're going to say run until complete the main function. So it's going to stay on, and it's going to receive requests until it completes or until we exit. So there's no real completion, but rather an exit. Okay, so that's going to be the last piece of it. So what does this look like? If we open up the file in inside the servers ML_model, then we're going to see here the imports that we had, the class that we selected, and then the implementation at the end, the if name equals main, and so on. All right, so now the way in which we run it is in the same way as we run Python files. So I'm going to exit here from the Gradio app. I'm also going to end the fast API server that we had earlier. So right now I am inside the servers. I'm going to go one back, and then I'm going to say Python servers ML. Oops, I need to go one back to cd do. I'm going to do Python servers ML model, and then MLServices. I'm going to create that service. So notice what's happening. Also, don't pay attention to the TensorFlow errors there. I should have deleted it from this environment. I was testing something, so my environment is not going to have the same things as yours. Let me see as well if I have any questions. Okay, no questions. So notice, so yeah, don't pay attention to all of this stuff. I have a weird version of TensorFlow there, and that's okay. But notice a couple of things that MLServer gives you. So it gives you a gRPC port where you can send requests and receive requests from via gRPC. Then you also have an HTTP server, which is what we're going to be using, and that is sitting at port 8080. And then we also have a metrics. What is my metrics? Then we also have a metrics server sitting at port 8082. Okay, so how do we do this? How do we access this music gen model? So the way we do so is we create a request. So notice what's going to happen here. Remember that I told you that MLServer follows a particular standard, set of standards for doing inference. And that standard is called V2 inference protocol, or nowadays is referred to as the open inference protocol. So we're going to import some codecs or some helpers to help us encode the request that we're going to send to our server. So let me show you what that looks like. Here we have three. So this string codec and this NumPy codec, they're going to encode the input. The input is going to be the exact same thing we were doing a second ago. We have a description, slow bachata with violin sounds. We have a guidance scale with number 5. We have max new tokens with the seconds. So maybe let me put this one at 280. And then this is the way these three are going to look like. So it's going to become a request input. The name of the input is going to be text. The name of that input is going to be guidance. So each one of those maps to the name of the input that the predict function takes. So then we come down here, and then we see that it says, oh, also it has a shape parameter. What is that? Well, it's saying here I have a list of one element. So if you think about it, it's going to be one row, or it's going to be a batch of one, and then it's going to be one element, one piece of string. And then we're saying using bytes false because we're going to send that piece of string. So it says data type bytes, but hold on a second. And then the parameters say the type of this content is a string, and then no headers. And then it's going to send in the data, it's going to send a tensor data. And it's going to say slow bachata violin. To actually have a look at it, we can do this instead. We can say, okay, well, actually show me the thing that I want to see. Show me the dictionary of this. So it's that we're sending a dictionary or a JSON object over the network, and where each one of these dictionaries represent the value that we are sending through for a parameter. Second parameter called guidance scale in our predict function has a shape of one batch, and then one element. It's an integer 64. The content type is NumPy array, and the data is 5. I'm sending a 5 for the scale. Now, if we want to, the way in which we actually process it is we put inputs in a dictionary, and then we pass in a list, what's going to be the first request. And this is what it's going to look like. So each one of the three, text, guidance scale, max tokens, is going to take this one, this parameter here, and this 200 here, respectively. So now we can pass in, we can also do it like this, as opposed to the way in which we did it before. So before we pass in all three right here, but then we can also pass them in here, the three objects that we created earlier, and that's also completely fine. And then we have an endpoint. This is very important to pay attention to because we're going to be in localhost 8080. That's fine. We've seen that before in the applications that we created. We're going to use the V2 inference protocol, which says that we have a models directory, a place where all of our models sit. Then we have the name of that model that we gave it. Notice here that it says loaded musicgen _ model. And then we have a method called infer. And then that method takes in a post request where we send in some data and we receive a response back. So here we're going to send the request as a post request, and then we're going to pass the endpoint and the inputs that I showed you a second ago. So now that's going to start running. It's going to take a second. Remember that it took a little bit earlier when I ran it in my machine. But the idea is that we have our first microservice created. And now, once the call goes through successfully, we're going to see down here a OK 200 status because the call went successfully. Or sorry, the post request went in successfully. Then, once it finishes, we're going to get a JSON output. We're going to be able to see a response object similar to the one that we use to send in the request. And then after that, we can evaluate what happened, what's our audio sounding like, and see if we like it, and see if we want to tweak it, or if we want to use it for something else. Let me see if I have any questions. Does he keep the NumPy array shape when encoding and decoding? That is an excellent question. So it does keep it when encoding and decoding. And if you don't use the class to decode it, say, for example, an array of shape 4 and 10,000, so 4 rows of 10,000 values, then you will have to take in the shape and reshape it yourself. So NumPy array dot reshape, and then use the reshape. So it always keeps it, but to decode it specifically to your needs, if you're getting more than one array, you can decode that two ways. And I don't want to confuse you there, but I have two examples in which I show you how to do both, how to take in the shape that it returns back to you, and how to use one of the methods to get the exact same object back, just a straightforward NumPy array. Okay, so we have the response here, and it came through successfully. Let's see what our song. So here's what we get. So to answer your question, now here's the shape. It returns it back. So we have one array of 126,080 values in the form of NumPy. Here's the array. And then notice that I took the array as is. I pass in the sampling rate from earlier. And that's the song that we get. All right. So I put here a little exercise, but I know it's been an hour already. So we're going to go on our second break. And then since it is 2:11, let's come back at 2:20 and then keep going with the next piece of our section. In the next piece, we're going to create the visualizations to evaluate what's happening with the sound of the music that we created. In the next one, we're going to add different kinds of effects to the audio. And then in the last one, we're going to create new representations of the audio to play with it as if we were musicians or DJs. All right. So we'll be back in 9 minutes, 2:20. See you soon, everyone. Michael, so where exactly are you at? Are you a little bit ahead? I also have been having troubles with saving files. Okay, I wonder where both of you are at, Leon and Michael. You might be a little bit more ahead, but let me see. Save files. Oh, okay, hold on. Is it here to save the file? In make sounds. Okay, let me see. Make sounds. Let me try it. It's probably the same error. Helpers that make sound and opening file. I have to use the full path. I didn't have to use the. Okay, let me see. Ah, okay. So remember, I think so. For me, it worked fine. So remember that you have to have. It doesn't know where the notebook is, so it doesn't have that context. So if you run the, let's see. Remember that. Okay, so the thing that I'm thinking is that remember that you need to have this server up and running for make sound to function. Make sound is where are you? Main sound, make sound. Okay, so helpers. So make sound is making a call to um, to this to this endpoint here, to the server. So if you don't have this one up and running, the one that we just created with MLServer, then it's not going to work. So that might be the reason. Another one is OS. So that's going to be import. Like you should be able to import this without a doubt. Then I'm saying that music. Both of you, I cannot remember if the music directory has been it's on the repo. If it isn't, you need to create a music directory. Otherwise, it won't find it. Let me see. It's here. No, there is no music directory. So make sure. Okay, so two things. One, make sure the server is up and running with music gen. Two, make sure you have a music directory. Otherwise, it's not going to find where to put the song at. I think I might have put something about the music directory somewhere. Let me know if that works. Okay, you have the endpoint server running, and I think that may be okay. Yeah. So check it out. At the endpoint and see if that fixes it, because I think that might be the issue. Also, make sure you add a directory called music. Leon, I wonder what is. I wonder what might be it. So you have the server running, and you also have the music directory in. So for example, when you come, let's see, distortion. When you come up here and you do, well, yeah, PWD, you should have just for after parallelism has already avoid using tokenizers. What the heck? So yeah, you should be inside the tutorials. Sorry, not the tutorials, the ML microservices, and then inside the 2ML web app P1. That's where you should be at. And then inside of that one, then you should be able to see the music directory. And if you haven't created it, then you need to create one of these ones so that it knows where it's going, because the helper is saying, hey, there should be a music directory here, and I'm going to join that directory with a fake name. So we're passing in any kind of name whatsoever to the music that we're creating. I think also if you're in Windows, then you might need to change this, because it's not going to be, Windows doesn't use forward slashes. It uses backslashes. Awesome. Thank you, Michael. Perfect. All right. So I have a little exercise here, and we haven't really stopped to do one. I do know that we have about, if I'm not mistaken, we have about 40 minutes together left. Let's see. Yeah, we have about 30 minutes left. So what I'm going to do is I'm going to keep going, and then I'm going to leave these exercises for all of you to finish on your own. Okay, so then we're going to jump to the visualization. So there's many ways to visualize sound, but here I put two. One is a waveform, and another one is a spectrogram. A waveform is a visual representation of sound. It's similar to what I showed you earlier in my awful drawing, but just to give you an intuition of what it is. And they're like a musical blueprint. So they help, which will help you visualize and understand the language of sound. Like, where is it going? Where is it moving up? When? How fast? Where did it have a peak? Or where did it have the biggest peaks in the tone of the sound? When did it go down? And so on. And then the spectrogram is a visual representation of it, and it becomes an image. Is where sound becomes an image. So when you talk, sing, or play music, these waveforms represent the vibrations in the air, and then these waveforms pasted into a continuous representation or image that is going to become a spectrogram. So it's the visual representation of sound waveforms. And then, so what we're going to do is, instead of using PLT to create an object, we're going to use the figure to create an object, because that is what we're going to pass into our application in a little bit when we create an image. So here we have matplotlib, and we are saying, hey, we're going to take in a waveform. By the way, I stole this function and adapted it from the PyTorch, the Torch audio documentation. They have amazing documentation. And I mean, this just gets it done. So they didn't have it as a figure. They have it as something else. So I did a couple of things to it. But all in all, I did take inspiration from them. So you take in two parameters, waveform and the sample rate. You take in the shape, because here you have the channels and here you have the number of frames. So compressing the number of frames by the sample rate is when we get the seconds. How many seconds do we have? And so on. So then we take a numpy array from 0 to the number of frames, and then we divide it by the sample rate. And this is the time axis of our visualization. Then we create a figure. We pass in subplots. So if we have different channels, we're going to have two subplots. If we only have one channel, we're only going to have one subplot. So it says if num channels is equal to 1, then axis equals axis in a list. So for C, in a range of the num channels, so channel 1, so we pass it here. Then we plot the time axis. We create a waveform. We pass in the waveform, and then we pass in the line width of 1. Then axis 2, grid true, and then we say if the number of channels is greater than 1, then we're going to pass in the label, and then we're going to say C plus 1. We pass in the subtitle of waveform, which here I can give it a capital waveform, and then we return a figure. We can do the same for spectrograms, and in reality, this is doing almost the exact same thing. But in matplotlib, in the first one, we're doing a regular line plot. And then in the second one, we're doing a spectrogram class. We're using the spectrogram class. Now, if we take the result, so notice what we got here earlier. We got this long dictionary where the output key has a list. So we're going to take the first element, and then the list has a dictionary. We're going to take the key data, and then we're going to have that that array of sound. And then so that's what we're passing here. So this also ties back to your question. I think it was Nan that asked it. Yeah, so Nan, this ties to your question. Lloyd, actually, I just arrived yesterday from Australia, so I'm very jet lagged still. But thank you for being kind with the time frame. But I am here in Austin, Texas. I am in Austin. But I am quite jet lagged too. But I'm okay. Thank you for asking. So we Nan, this ties to your question. Do we need to recreate the array? We can recreate the array, and then there's other methods in the codex where we can decode an array and get back a NumPy array. So here we are creating an array from the data, and then we have the sampling rate, and then we created a figure. And then here we have another one, and we created another figure. I think for this one, we do have to do plt.show. That didn't really... It didn't really end up showing it, but that's okay. We're about to showcase them. Let's see. That's weird. If we put here plt.show, taking this out. There you go. So here's the waveform. And then if we do the same for this one, let me take in the plt.show. I think I'm not passing it correctly. Let's see. So this is one. Then the sampling rate is going to be 32,000. He doesn't like me. Very interesting that I am unable to see these two visualizations here for some reason. But that's okay, because it's expecting a shape, and then it wants the number of frames and the number of channels. Okay, that's fine. So what we're going to do is we're going to pass in this in the SRC plotting file here. We're going to pass them. We're going to put them in here, the functions. So this one, notice this. This is saying get the latest files, and we're passing it here, get the latest files to each one of them. So what it says, what that means is that whatever song we created last, Brazilian noise, Emily Watkins, Alexander, H. Alexander, or whatever song we created last, is going to say, find the time, the latest time, find the maximum time of when these files, or the closest time to now when these files were created. Taking that latest file, pass it to my audio file, and then read in the frames, give me the sample rate, and return this too. So that's exactly what we're doing with these three, and then we are appending them to it. And then what happens is that once we get to our application, so I do have it open running now. So if I come here, so this is the song that I created a second ago, the one from the example. Let me zoom in a little bit. And if we want to visualize that, then this is the waveform of that 3-second audio file. And then this is the spectrogram of that audio file. And the reason I pick XKCD is because I think it looks quite nice. And notice here that it's kind of truncated. Of course, it doesn't have 0 seconds, the song, but it starts at 0. And then it doesn't have particularly 4 seconds, but it has like 3 and a little bit. So it gets all the way to 3 something to where it ends. And that's quite nice. And then here we see something similar, but in a spectrogram, and see like where are the magnitude, like where is the highest magnitude at? And it seems like it's kind of like at the beginning where the highest pitch are at, and then at the very, very end. Then here it kind of tones down in the middle, and so on. So that's just a nice way of seeing what we have. Then the third piece that we're going to create for our microservices tool or platform is the audio effects. So I remember that I mentioned that MLServer is not just about machine learning, but it's also about anything that you want to create that has to return something back to you. So here we have the audio effects. I put a little description as to what they are and how to think about them. But we're going to do something similar to what we did earlier. We're going to have different methods. So here I have delay and pitch shift. So here I'm saying delay the song by 0.25, but actually I'm going to put 35 here. Mix 1.4, pitch shift, seminodes, I'm going to put 9, and then gain decibels, I'm going to put 4. I'm going to create an object. Oops, I need to instantiate the mix. Mix must be between 1 and 0. So that's how you can tell how much I know about music in and of itself. So here we have the pedal board instantiated, delay and pitch shift. So remember the sample rate from the song we created earlier. This is the song that we created before. Here is the song without any delay whatsoever. Without any effects whatsoever. And here's the new song with delay and pitch shift. So quite different and very, very different. And I still have long ways to becoming a DJ, but this is one of the cool things that we can do with Pedalboard. So now what do we do? How do we create a service for it? Well, in the same fashion as we created the one before, we can say we can do our imports from Pedalboard. Then we can import from MLServer the tools that we need. Notice, remember, I mentioned I was going to say a couple of things about the decode args. When you wrap this decode args over here, it understands a couple of things. It understands NumPy arrays. It understands pandas data frames. It understands bytes. It understands a list of strings. And I think I'm missing one more. But there's a very constrained, or not constrained. There's a few elements that it understands very well. And usually you can represent almost anything as numbers in a computer or as bytes, if not one or the other. So you can pass in anything through it, but remember that you have to specify for it to decode it, you have to specify the type here. If you don't want to use that and you don't want to pass in the type, you can avoid that, but you will have to do, you will have to send in your request in a different kind of way. So what we're doing here is, I know for a fact, I want my audio mixer to have a delay and pitch shift, no matter what the song is. And then in the second one, I'm saying, well, I want the song to gain nothing, no decibel. Actually, let me change this one a little bit. To gain 1 decibel. Then I want to pass into the pedal board. I want to compress the song, and then I want to create a mix between the pass through and the delay and pitch shift. And then I want to add some default parameters of reverbs to make it sound like it's in a wide room or whatnot. And then I'm going to pass the song through my board using the sample rate, and I'm going to return the new piece of audio. So that's the essence of it. Now, there's 3 things that are important to keep in mind with MLServer when you create custom models. Earlier, I showed you the way of creating one via one single Python file, the one that we have running right now. So these 3 pieces here become one Python file. So that's one way in which you can run MLServer. But one of the most common ways of doing it is that you have a directory. And then in that directory, not there. In that directory, you have, so for example, here I have servers, and then I have pedal board, and then I have audio mixer.py. You have a .py file with your model settings. So you're loading something here. Here I'm just saying I'm loading the effects that I want for certain. And then you have the predict method where you're going to take in some input and return something back. And then you don't even need to put anything else after that. That is going to be your audio mixer.py file. But then you need 2 things. You need the models-settings.json file that we saw earlier. Earlier we saw it as a class. Now we're seeing it as a JSON file. So it says the name of this model is going to be novice DJ. The implementation is going to be the name of the file up here, audio mixer.py, and the name of the class, audio mixer. Similar to when you run Ubicorn, you give it the name of the file, and then you give it the name of the app. And then here we are saying in the settings, so this is the server-wide settings. We're saying, hey, I want a server with this port for HTTP, this port for gRPC, and this port for the metrics. And then if we come, so let me actually run this 3 to make sure it is there. Oh, appending service. No, not appending. Actually, yes, appending. Okay, so if I come and check my server in pedalboard, I'll see that it has everything I need. Here it is. And I actually don't need the typing optional. We could take that out of there. In here, we don't really need that. Have it like that. All right, and then we can come here, and now notice the difference here. Earlier we used Python to initiate the service. Now we are going to use MLServer itself. So I'm going to move into my directory, and I'm going to use MLServer start servers pedalboard. I press start, I press enter, and then notice that it loaded my novice DJ. And now I have another server up and running at port 750. So now let's check that that works fine. So I'm going to create another request, and I'm going to say, this is the song that I want to pass in, the one that we created earlier, that we passed in the effects a second ago. And then I want to send the sample rate as well. And then I put it inside a NumPy array. These are my inputs to my request. You can check that this was created successfully. So this is what the big array looks like. This is what we're sending through. And then we pass it in to our post request, 750, the port. Let me open here so that we can see that the request is successful here in a second. Then we pass the JSON object. We get a response back. We got a 200. Down here, we get a 200 as well. That took about 2 seconds. And then we can check in how that sounds now. Very nice, very nice. And then if we check so this is the original one, remember, and then this is the new one, the one that we're about to listen now, to now. It sounds more like a live concert than like a performance. Here it sounds like it was recorded. And then there it sounded more like it was a live presentation. Okay, so last piece of the app, and then if we want to test that it works, here's what we can do. We can add some effect, and then we can update our music. So remember that our helper that we saw a second ago, where's the helper? SRC helpers. So we have here two functions. One is called make sound, and another one is called audio effect. And we'll walk through them here in a second. But what we're doing here is we have the endpoint that we just hit. We have, we're looking for the files inside the music directory in here. So all of these songs have a timestamp assigned to them from when they were created. So we're getting that timestamp. We're getting the maximum one for all those files. And then we're taking that latest file. We're opening it up and reading it. We're taking the sample rate. We're passing in those two values, the waveform and the sample rate, through a request. We're sending in we're sending in a request. We're getting back an array, and we're making a waveform here. Did I keep that? Let's see if, yep, I still have a bg.png. If you don't have one, that's fine. This is going to create that, oops, gr is not defined. So if you have an error in that, okay, I think I found it. If you had an error in audio effects, then it's because in helpers.py, I am not importing radio. So import radio as gr. Make sure you do that as well. Okay, so now this is up and running. Let's go back to the app. Let's see if this works. So we got to create a song, fast bachata with violin sounds, okay? Then also you can tweak the max number here. Let me see if I have any questions. Okay, connection error, HTTP pool host localhost port 750 max retry exceeded with curl. Novas DJ cost new connection error. Failed to establish a connection. No, Michael, that's a great question, but it should take the make waveform, because that is going to make like a little video with a waveform. Let me see if it finished, and I'm coming back to this question. Gradio here. GR make waveform, yes. Okay, it did say reload work may fail. Let's see if this works now. And then Murthy, so you had a connection error, an HTTP pool host localhost port 750 must retry exceeded. It's the new connection error. Which command gave you that error, Murthy? Can you share in the chat with me, please? Okay, perfect. Run MLServer command. Okay, excellent. Let's see if this one comes up, because this is the last bit that we have. So we're gonna create a new song, see that this one works, and then see that the update your music also works. That is taking quite a bit of time. And the request was already successful. I wonder what's happening there, but that's okay. We can move on. So that request says it was successful. This one was successful. Okay, we'll come back to the application here in a second. But now that we have the last server up and running, so remember, there's two ways of running these servers. We can create a directory with 3 files: a model definition, a model settings.json file, and a settings.json file with the server level settings. Then we use the NumPy codec to send in the arrays of numbers, and then we get back the response. We check that it works, and it works fine. Now we're going to do MIDI representation. So from an audio programmer's perspective, MIDI is, or musical instrument digital interface. These are representations of digital language that computers and musical instruments use to communicate. So to some degree, it can be much easier to update, tweak, and play around with MIDI representations than it is to play around with numbers per se. You can do a lot of things to the numbers, but you also have to be quite clever on how you're going to do it to a specific seconds. So right now, we're applying effects to the entire array of audio. But oftentimes, if you recall DJs, how DJs work, they're taking a piece of the song or a moment in time in the song and applying an effect to it. They're not applying effects to entire songs over and over and over and over. So MIDI allows you to do that quite well. So here we're going to import a IPython iframe object, and then we're going to be using basic pitch. So Spotify released an open source tool called Basic Pitch, and then they also released a website version of it where you can come in and you can try the demo right on the website. This video right here is fantastic. This person, her channel is Bad Snacks. I think it is Bad Snacks. And the video that she recorded going over basic pitch is phenomenal. I really recommend that you check it out if this sounds interesting to you. But let's try the demo. And then let's click here, drop your file. We're going to find a song. From this big thing of songs. Let's see what it does. So he's going to load it. He's going to convert it to MIDI. And then we can play it from here. And now, so this is the MIDI representation. And now what we can do with it is we can show the adjustments that we can do. So we can do note segmentation, and then split nodes, merge nodes, model confidence threshold. Well, let's do more nodes, fewer nodes. Well, we don't care. We're going to put it at 60. Minimum pitch, let's do a little bit. Ooh, that's high. The minimum allowed pitch in hertz. Okay, we're going to do 50. Maybe 110. Okay, that's fine. Maximum pitch, 2450. Minimum note length. MIDI file tempo. Okay, that had a higher tempo, so let's reduce the tempo. Okay, so now that I have those adjustments, notice how my MIDI, I wish I would have been able to show you how the MIDI is being adjusted as I move it. So let me zoom out a little bit. So notice that if I move this, then the MIDI notes start moving as well. You can see that some disappear and some appear again. So now I can play, you can play it again. As you can see, like you can play with this and create really cool representations of your music. And let me see if this one got created. Okay, that took quite a while for some reason, but that's our song. And then to check out, to visualize that, here it is. To get the spectrogram of it, it seems pretty straightforward. It keeps the same tempo the entire 5 seconds of the song. And then here we can add some effects to it. Let's see if this works. Yes, it did work. And then let's see. That was not great, by the way. I think it made it quite worse, but that just shows my level of DJing skills is not very up to speed. Then in the last part of this microservices architecture, remember we have one piece, we have a model generating music. We have another piece where we are creating visualizations. That is part of the UI because we can put it there. It's not expensive to have, it doesn't require that many resources or enough resources to have a separate service for it. For the second service, we do have it as an API. So the first and the third are both APIs. The fourth one is the media representations, and we're taking an iframe from a website openly available that allows us to add files to it and then do cool things with music. So those are some of the things that we can do with this microservices architecture. The next one that I don't think we're going to have much time for. So this is another one, and then you can pull out the notes to tweak them, and then notice how this starts. So you can really do amazing things with MIDI representations. Okay, but in essence, there's a lot of things that you can do with music, and there's even more cool things that you can build with microservices. And that way, like say for example, if you're doing your own pet projects, and it doesn't necessarily have to be a pet project, but you're doing some sort of project and you're working on different components of that project. One day you might feel like working on building the model, training the models. Another day you might feel like building the UI. Another day you might feel like, hey, let's actually spend some time thinking through the architecture of this system. How should this API talk to this other API? So you can also work in you can work on one project and make it different projects at the same time by breaking down your architecture or your application into different microservices. And then the last piece is also MLServer. MLServer is quite nice because it allows you not only to create one model, but it also allows you to do multi-serving very easily. So I want to give you an example. If I was to copy, or if I was to bring because I know we're running out of time, so I want to show you another example. If I was to bring in this is my turn. I have the novice DJ here, and then I have the model generator. But if I was to bring in here another server from the next session that we had, servers, say for example, I do the audio embeddings, and I'm going to put it here in the servers here. So now I have two different kinds of models that MLServer can go ahead and find. So if I do here, MLServer start servers, then I have to let this one go too. If I do MLServer start servers, let's see, from pan inference, no model name, pan's inference. Let's see, we're going to do a different one. Okay, so what I did there was, because I was using a different environment for the model settings that I brought in, notice that I just took a different model from the next section of this workshop. So I have pedal board, I have the ML model that we created earlier with music gen, and then I have a music classifier here. If I come in here to the music classifier, you can have a look at it, the implementation. It's called music classifier. Here's the name of the class. Here's the name of the Python file with the music classifier class. And here are the settings for that server. So if I do now MLServer start servers, notice what's going to happen. So MLServer is going to take in every file in those two directories that have the music classifier and the novice DJ, and it's going to create a model for each one of them. So now I have one endpoint for both of the models. So I can do the things that we were doing earlier. So when we were taking this endpoint, one endpoint like this one. So now what we can do now is we can use one single endpoint, 880. So if MLServer detects two or more different server level settings, then it's going to default to port 880. And then if I change this now to 880, I could send in a request to the novice DJ. And then I could also say music classifier, which will tell me what exactly is my model. So let me give you an example. I'm going to send in that request with, let's see, what do we have here? Sampling rate and the audio value. So if we send it here to 880, and we're still going to get an okay. But then if I send another request to, hey, what kind of music is this one? So I'm going to change the URL for music classifier. And then I need to take out this one here because the music classifier only takes a song. And notice this, the music classifier also. So now I have two models in the same server with the same resources. And now I can save a little bit. You could save potentially a little bit of money. If you have multiple models in the same server, you can use one specific framework to build your models, and then, or two frameworks to build your models, and then the same framework to build it or to serve them as microservices. So I hope that was useful. I think we're running out of time now, but let me check. No, the PNG, the background one was not in the repo. I'll add it, but just so you know, the background picture was a black image for the. So if you don't have any, I think it's still gonna show it. You're gonna get it. I think you're gonna get that image. So that one was white, and then if you don't put a white background, you can put any color in the background that you like. But yeah, I'll add it to the repo regardless. And I think there's another one where you can make this animated, the little video showcasing the music, but this wasn't a really good music, so I'm not going to play it again for a really good song. But the last thing is that piece is, so the command I used was MLServer start servers. So now, remember earlier, I was going to each individual directory. So pedal board, I was going MLServer start servers and then pedal board. But now I'm going MLServer start servers, and then it's going to look for all of the files inside this directory, and then it's going to run them. But they have to be in a specific files. So it didn't run the ML_models because everything is inside one big Python file. Because these ones were separated into model settings, and model specification, then we were able to put them, it was able to read them all because it found the things needed to read in those files. Okay, so I guess we'll stay until we get kicked out. I know we're coming out of time, but let me walk you through the application in Gradio because I haven't talked about it, even though I just showed it to all of you. So the application has a few components. And I think the coolest thing about the application is that it has a lot of good functionalities, but it also has the XKCD theme. I think that's the thing that drew me into using Gradio for this demo, because the next demo, we're not using Gradio at all. In the demo for the third part, we're using a tool called Nice GUI. I don't know if any of you have heard of it, but let me finish with Gradio, and then I'll walk you through the next one. So in Gradio, we are importing the helpers that we created a little bit ago, and then the tools, the plotting tools that we created as well, and we added to the source directory. Then we are adding something that Gradio called blocks. And then in this blocks is where you can define the theme that you want to use. And I put the XKCD one. You create a tool or a context, and then you name it demo. And then you start adding pieces and components that Gradio is going to understand where they go. So you have objects that you can use. So here I have a column, and then I'm adding in that column the step one. Then in a row, I'm adding two elements or a couple of elements. I'm adding in a row, I'm adding a new column, and I'm saying, here's a text box to describe the song that we want to create. Here are the values of that song. And then we're going to say, make that music when they click this button. So then we're saying, also give me another column. And then in that column, we're going to have tokens, guidance, and sample rate. Those are the three parameters that we can pass in to our request. Lastly, we're going to have an audio file. And then notice here, that audio, this button here is going to be attached to something called a callback. A callback is a function that we can reuse over and over with certain actions. And then usually when we rerun that function, we get something new happening. And here we are calling the function make sound, which is the wrapper that you saw in the helpers. So this wrapper make sounds takes in the piece of text, the number for the guidance scale, the max new tokens, and the sample rate. It has the endpoint that we were using earlier. It has it passes in each one of these components to its respective encode input encoder. Then it sends in a request to the server. It takes in it transforms that response into a NumPy array. It saves the file in our computer with some random name that we're creating from the faker module. And then we return the sample rate and the audio array. And then there's another one called audio effect. This one is doing the same as this one above, but it is not saving the file. And it is also taking the latest one that was created, finding it, and then sending it in as a request and adapting it so that we can use it, so that we can play it. So it's saying make waveform, and then it's playing that as we saw in the background. Okay, so those are the helpers that we're using in the application. But then here, this make music, this button has a click, and then it's going to rerun a function that makes sound that we just saw. That is going to take several inputs. When people put them in, they're going to have default values. So the text box has a default song description of a fast bachata with violin sounds and few notes from saxophone. And then the guidance has a, here it is, here's the guidance scale, has a value of 3, minimum of 1, maximum of 50. Then the max new tokens has a value of 200, minimum of 5, maximum of 1,000. Same with the sample rate. It has a value of 32,000, but it only gives you the user the option of having 3 kinds of sample rates. We pass in those inputs, and then we get something out. That something out is going to be this object here, this audio output object. So we're going to pass in the song that we get back into this button there. It's kind of interesting to wrap our heads around how to create reactive applications to actions in a website. I feel like once you do it for a little bit, it becomes second nature, and you never even realize that it was difficult to learn. But when you start learning it, it becomes it's interesting to wrap your head around it. Anyhow, that's the first block. So we still have 3 more blocks. So that's the first block for creating music. The second block is for creating the 2 plots. We have a description here. I added an empty markdown to add some space in between the components because they were way too tight, way too close to each other. So we're creating the plots. We're saying when a person pressed this button, we're going to have a button object. But then when a person press this button, we're going to run that function make waveform. And the output is going to be this object here. Same with the next one. And those are the visualizations that we saw. And then lastly, second to last, we have the add some effects. We have, again, a button. Then we have a little video and the element ID of the video. And then we have on click, create an audio effect. Send the latest song we created, send it to our server, and then give us a video back. The last one is insert the iframe from basic pitch and let us so that we can interact with it. And then we have demo launch. So all of that entire application stays within a with statement. And that with statement, then we pass it back at the end. We give it the method launch, and then we launch our Gradio app. Okay, so I had a bit of an exercise here. So I put here install the diffuser package, import the audio LDM pipeline object, come up with a few prompts, put them here in a list, download the smallest model that you can find there, instantiate a pipeline, create a pipeline object with your prompts, and then create a server using MLServer. So I gave you hints here on how to do it. And then with the MLServer one, you can go and copy one of the settings above, and then run through it yourself. Okay, so there's quite a few things happening in the tutorial, in the last tutorial, but we'll walk through it until we get kicked out, because I think we're at time, but that's okay. Okay. So in this one, we have a lot of microservices. We have about 5 different microservices. So I'm actually 1, 2, 3, 4, 5, 6. So we have 6 different microservices here. And the idea is that part 3 is about creating different services, creating a UI for them, and then creating an inference graph. So for example, we have a piece of audio, not necessarily that we created, but an audio that we like, or something that we like. And then we take that audio, we decompose it. We take the instruments and we take the vocals. And then those vocals, we translate them or transcribe them into text. Then from that text, we create embeddings. From that embeddings, we can create a recommendation system. Then go back to the audio. That audio, we give it some audio effects. We combine it back with the transcribed version or with the vocals. And then we see how the vocals sound when we don't change them, but when we change the audio. And so then we can apply to the text, we can apply sentiment analysis, or we can create audio representation, audio embeddings from the audio itself, from the songs itself. So let's see how far we get on this one. Here we have the same song from earlier, and we have a few things here. We have the demox.api. The demox is a Python from Meta for splitting sounds and vocals, and it gives you 4 different characteristics or 4 different sounds. So here we're saying the demox API, we're creating a separator. We're putting it on the CPU. It's actually quite fast, even on CPU. Then we're saying from torch, torch from NumPy array, because our first song, remember, pedal board returns NumPy arrays for the songs. Then this is one of those interesting ones that it requires that the song has to have 2 channels for it to work. Okay, so here we have the original song returned to us, and then the results. So the separator is going to be a dictionary of drums, bass, other instruments, and vocals. Let me stop this service. And this one too. And while this loads, I can actually show you what the UI for this one looks like. So something to note, I put this one in this one here. There is a mismatch of dependencies between MLServer and Nice GUI. MLServer has a pinned down version of Fast API. Nice GUI has the, I think it always does the latest and greatest version of Fast API. So there's a mismatch between the two. So I put here another way to create the microservice a new environment to run Nice GUI. So it is going to be the app here that we have called main.py, and I'm going to say Python main.py. I might need to import matplotlib or install matplotlib. Okay, there it is. Oh, the thing is that I'm in the wrong directory. Okay, so here's the application, music platform, a new way of finding music. The purpose of this app is to showcase one of the many cool and fun ways in which you can create machine learning microservices for different creative purposes. So here we have a massive list of songs, about 12,000 songs. You're going to recognize a lot of them. You might not recognize a lot of them. For example, okay, yeah, so this is a good one. Let's find Elvis Presley. So here's Elvis Presley. So here you have the name, the name of the artist, Elvis Presley, song name, Until It Is Time for You to Go, genre, blues. All right, so let's go back down here. So that's our nice GUI app. We have 5 different tabs, but not all of them are finished. There's about 2 of them that are finished, and then the other 3 are meant to be for exercises. Okay, so let's walk through the app, and then also let's come back here and see our music separator. So here's the music separator. So first one, we have the drums, then we have the bass, then we have other sounds, and then we have the vocals. So this is for the song that we heard before in the previous section, the first one. Let me see here. And then if we come here, notice the drums, and then the bass, other sounds. And notice how you're expecting a bit of music or some sort of voice to come out, but then nothing comes out. And then the a cappella version of the song.
It's an automatic pay as you go. You won't get too far if you ain't got the dough. Way down in debt, your chips have been fried.
So very cool. And now that we have that, the splitter, we can create a server as we did before. So here we are creating one called song splitter. Then we call it the model. We don't have to call it a model. We can call it whatever, anything we want. We are instantiating or loading the weights of the separator. And then we're saying this is quite an important piece to notice, because you are creating with MLServer a class where MLServer itself recognizes or sees the predict and the load as the two key parts that it's going to look for. You can also create other functions that what they do is that these functions, what they're going to do is that they can do pre-processing of your data or post-processing of your data. So in this one, we have a case of post-processing. So we're saying self, post-processor, result, and so on. So what that does is that before we send it back, we're going to create one new key in that dictionary, and we're going to call it instruments. And we're going to combine the bass, the drums, and the other into one called instruments. And then we're going to delete those three because we don't want to hold all of those arrays in memory. And then we're going to use torch vertical stack to stack the vocals and then the instruments. And then we're going to return that as a numpy array. So that's what we're doing for the splitter. And we have here the model dash settings, music splitter, split them underscore models, and that song splitter. And then here we also have the settings for the server. So if you want to run that, we can do, I have to go back to the third. We can do MLServer, start, servers, splitter. And there it is. Our music splitter is now loaded. And we can now send requests to it. So notice that we have it at port 510. So here is the port 510. And then we're going to send it through with the song. So our first song is the one that we had earlier. And actually, one of the cool things about this is that you can come here and you can also click download to the songs. So I'm kind of tired of listening to that one that we were listening to. So we could come here and pick another one. Let's see if they have Bob Marley. Would be cool to listen to. So by the way, this data set here is going to be, you can find it. I have a link in the notebook, but you can also find the data set in Kaggle, Ludwig Music. So it's called the Ludwig Music Dataset Moods and Subgenre. So this is the one. And you can see in the directories the kinds of labels that it has. So what I did, one of the services here, the music classifier, is it's a fine-tuned model wave to back that I use to fine-tune it on this data set. So there's about 12.83 gigs in here. Not all of it is to the MP3 songs because it also has the spectrograms. But the 12,000 something songs, they are going to have about 2 to 5 gigs in them. So be careful when you download it because it's going to take quite a bit of time. What I did was that I added the songs to a public bucket in AWS. So you can use the dataset that you see here, the payload.csv, and then here, that is sitting on a bucket of mine in AWS. So when we send, when we use the UI right now is looking for those songs, the URLs for those songs over there. And we're going to go and talk about the UI here in a second. I wanted to see if they had something of, if there was something of Bob Marley here, but it doesn't seem like there is one. I hope there is one. Nope, there isn't one. Okay, we'll take any of them. Let's see if Toxic is here from Britney Spears. Oh, yeah, it is. There you go. So that's the one that we are going to download. So that way we have a different one to use with our next model. Okay, so we're going to come here. And now that we have the server, we can test it with the Britney Spears song. Six. Here. And there's a Britney song. Now we can read it. We can copy the code here. And then before we test it, what we can do is put it up here and change this for the one with Britney Spears. There it is. And now we pass Britney to the splitter, and then we see if our server that we just that we instantiated or created a second ago, if it is working as intended. The next one, while that loads, the next one is a transcriber. And the transcriber is going to do exactly what you think it's going to do. Now, the cool thing about the transcriber is that if you do it on the plain audio, as opposed to with the vocals, it doesn't always guarantee that it's going to be better. But by definition or just by intuition, you would think that if I have a song and then I have lyrics in the song and I split the instrument and I leave the lyrics on, if something is trying to detect the words that are being pronounced, it should be easier to detect them if there's no background noise or background sound. But that wasn't the case with the experiments that I ran. I bump into a few things or a few songs where the transcription or the decoupling of the vocals with the instruments didn't make the transcription better by any means. Actually, in some instances, it even made it worse. Okay, so now we have the song here of Britney, and it is working perfectly fine. And if you, there's one more thing that I think is one of the coolest examples that you can do with MLServer that I think is worth showing here, in particular before somebody calls us out and says like, hey, the session is over. And I believe this one is right here. So this one is part of a exercise. So imagine that we have taken the transcription of the Britney Spears ones. So for example, let's actually come back here and we're going to transcribe the Britney Spears one. Here I'm using the OpenAI Whisper medium size. That one is going to take a bit of time because that model is about 2 gigabytes, I believe, in size. So it's not huge, but it's not small. We're going to load it. I already have it downloaded, so it's going to find it in my cache. And then we're going to take the song from Britney. We're going to create a function, and then we're going to take the song, and then we're going to resample it so that it is in the same sampling rate. Remember, we talked about sampling rates earlier, so that it is in the same one. So we're going to say first song, first sample rate. Resample this. Okay, here's my function. And then here's a new version of Britney's song. And now we're transcribing it with the pipeline. We're saying max new tokens should be about 2,000. So I'm addicted to you. Don't you know that you're toxic? And I love what you do. Don't you know that you're toxic? So it actually did a really good job, even with the song not being separated. So here is the server that we can instantiate with it for the transcriber, the one that we did above. Actually, we haven't done, let's see. Okay, so here are the things that we can send, the requests that we can send to the transcriber, but we haven't actually created it. So we need to move this one just a little bit up. I am going to start the transcriber. MLServer servers transcriptor, I called it. I'm just missing the start. Thank you, Jumo. So the next one, building an independent workshop app so we don't worry about getting kicked out. No, actually, I haven't heard about the time that we are running out of time. I think it was meant to be 3.5 hours, but in my calendar, I had only 3 hours for this block. So yeah, we're past 30 minutes of it. So I don't want to take a lot of everyone's time. Let me see if Jen is here, because I also know there might be other sessions that all of you want to go to. Jen, are you still here? Okay. So what I'm going to do is I'm going to show the last example that I think is really worth looking at. And then after that one, then we are going to call it a day. So here I have, we created now we have the ASR, or automatic speech recognition system, already up and running. I call them music transcriber. And then here we have the endpoint for that. And we can send the song from Britney, from Toxic, and just to make sure that it actually works well. So now we're sending the request. We're going to get a JSON response back. And then here we have the text embeddings. Here I have an example that I think is quite worth pointing out. With sentence transformers, what you can do is create embeddings for words. So here we got Britney separated correctly. So we are happy about that. So with sentence transformers, we can create servers. Oh, sorry, we can create embedding representations for text. That means that we can use that to search more effectively, to do recommendations, to do a lot of cool things. And so here's an exercise where I ask you to create the text embeddings.py, the settings.json, and the model-settings.json. And because I already have it in my local system, I want to show you what this would look like to send, say, for example, you have 10 songs that you want to send requests to, that you want to send them in parallel, the request. So right now, you notice that if I send them one by one, notice that this response took about, this song took about 17 seconds to be split into different ones. And the model has a lot of weights, and I load them all in CPU. So it's expected that it's going to take a little bit longer. So that took about 17 seconds. But what if I had 20 different songs that I wanted to send at the same time? Well, what MLServer allows you to do is it allows you to do adaptive batching. And you can say, I want to send all of these ones in parallel to 5 different workers. And now you're going to have all of them done at half the speed that it would take to do them sequentially, as opposed to if you were to do them asynchronously. So I'm going to show you an example of this. I'm going to do MLServer star and text embeddings. Notice that the server is 480 or 4080. So I'm going to do that 4080 here. And then the name of the model is text embedding. And I'm going to create that endpoint. The name of the file, let's call it lyrics. And then I'm going to pass in the transcribed version of Britney. Should put transcribed version in list. So I'm addicted to you. Don't worry that you're toxic. You know you're toxic. Yada yada. Send it to the endpoint. It is extremely fast. But then what if? Then we get the response back. We get the embeddings. But what if we want to send many at the same time? So what we would do is, let's say we're going to write a sample-txt file here, and then we have a bunch of dummy text here, the lorem ipsum whatever thing. So just for example's sake, but we can put the transcription of a bunch of songs. So we have about 14 of these ones. Yeah, about 14 of these ones. And then we wrote sample-text.txt. Then what we're going to do is, so notice that we have the sample.txt there with some data. And then what we can do is we can do MLServer infer-u and then localhost 4080. And then the name of the model, text embeddings. The input is going to be sample-text.txt. And then the output is going to be text-output.txt. I'm saying use 5 workers for this. So I'm saying a batch. And instead of taking however many seconds, this is going to take a fraction of the time. So notice this took 0.9 seconds. And then it says we use 5 workers, 3 retries, batch, interval 0, batch jitter 0, connection timeout none, and then here you can see that all of the requests were sent successfully to the text embedding model. And if we evaluate the text output, you can see the embeddings here, the values for each one of the text files. So that's really cool. That allows you to do a lot of good stuff. And then also, one thing that we haven't discussed, but is important, if you want to package these servers into Docker containers, what you can do is you can go to, let me go into the servers, and then I'm going to go into text embeddings. And I'm going to say MLServer. I believe it is build. So it's a wrapper around the Docker command line. So MLServer build -t here, and then I'm going to put Ramon Perez text embeddings. But before I do that, I need to make sure that I have a requirements.txt in my text embeddings. I don't have one, so I'm going to say new file, requirements.txt. I'm going to put sentence and that's it. That's what I need to do. I do MLServer build -t, or actually I think build, and then I'm putting the T before where it needs to be, -t. There you go. Now it's going to build a Docker image that I can use to serve anywhere I want. I don't need to use Seldon products. I don't need to use all the things. Of course, our products are cool, but you can use whatever you like with our tools, and that's one of the coolest things about it. But yeah, so now the Docker image might take a little bit to get created, but I think we can leave it here, and we can give you back the rest of the afternoon to go and see other sessions. I think there's quite a few people there. We've gone over, I think, about just about 40 minutes. So I appreciate everyone staying a little bit longer to hang out and to get a little bit out of this workshop. So if anyone have any questions, I'll stick around for a little bit. If not, I want to thank you all for joining me today. And hopefully I'll see you tomorrow at the conference and on Thursday.